let me get back to making the comments. Somebody sent in a request for extending the quiz. I'll deal with it after the class. Okay, let's now make some comments, okay? So comment number one is that, this is the area under the curve is finite, right? So we can see that. I mean, if you do the integral, you can. I mean, it's not finite. It's obvious because, well, should be because this is going to zero very rapidly. It's exponential fall off, but the area under the curve is finite, and that means that the amount of energy that is being radiated is finite. So that helps us, that resolves the ultraviolet, finite total energy. So this resolves the so-called ultraviolet catastrophe. You might say, what is ultraviolet catastrophe? The thing was that, according to classical statistical mechanics, the curve that you were going to get was something like this. So this was in the UV, you had infinite energy. So this is how you got infinity. So that solves the ultraviolet catastrophe. The other thing is that you can work out, what the maximum frequency is just by taking the derivative of the Planck distribution. And the maximum frequency is given by, well, it's related to the maximum wavelength by c over lambda. There's a factor of twice pi there that I'm ignoring. Well, you can just call this nu. And then this is going to be a constant zeta kBt over h. And this constant zeta has the value 2.822. And if you solve it, it's actually a solution to if you do the math, you find that this is a solution to the transcendental equation, this transcendental equation, okay? So this comes from maximizing this with respect to omega and then converting to lambda or something, okay? So this is the curve that I drew over here. So it's dependence on temperature, the maximum. And number two, that was number two. And then number three is so we need to find the total energy. What is E? And you can, to find what E is, it's convenient to introduce a variable that is called X, and that's beta h bar omega. And then you can show that the total energy is V by pi squared C cubed KB to the power 4, T to the power 4, this divided by H cubed. And then there's the integral from 0 to infinity of x cubed dx divided by e to the power x minus 1. And this you can call I, this integral, and this integral turns out to be, I think you need to use some zeta function technique. You can just look up the integral. I'm not going to bother, but it's pi to the power 4 over 15. And then the energy density, which is the energy per unit volume of the photon gas, is given by KB4 T4 divided by 15 C cubed H cubed times pi squared, okay, because of this pi 4 and pi squared, right? So this is the energy density. total energy density when you integrate over all the frequencies. So lastly, the thing that I wanted to mention is that, so suppose this is your black body, and you are looking at here at this point. So what is the rate of energy flux that is coming out here? And so that's the energy flux. And that energy flux is given by the energy density times C by 4. And this is equal to sigma times T to the power 4. The T to the power 4 comes from here. And then sigma is called Stefan's constant. And it's kb to the power 4 pi squared 60 c squared h cubed. And this factor of c comes from the fact that you're converting the energy density to a flux. Of course, the energy is going to come out at the rate of the speed of light. But what about this factor of 1/4? Where does this come from? So this comes from the fact that, our source of radiation is actually not a point source. And that what we are interested in is, just the photon coming out, not going in. And the way to, do this integral is to actually say, okay, so we have some, we have some sphere, and if we were looking at the energy per unit area, we would have to divide by 1/4 pi, but instead, because so here let this be the perpendicular to the sphere, but because our source is not a point source, it's an object which is much larger than the wavelength. There could be particles of radiation coming out this way, but what we care about is the radiation, the component coming out in this way. So if I call this angle theta, and then we have to integrate over phi here, then we have to integrate here over phi, which goes from 0 to 2 pi of d of phi, and then, but this angle theta only goes from 0 to pi by 2. And from the solid angle thing, analysis, we have to have a sine square theta factor. But since we're only interested in the direction of radiation in this direction, we have to multiply c by a cosine of theta. And if you do this integral, then you get c over 4. Okay, and that explains the c over 4 factor. And this law is called Stefan Boltzmann's law. Okay, so this is Stefan Boltzmann law. Okay. So I think this is the historical. This is an experiment of historical significance, and this is almost all I have to say. I have a few more things to say, which I will cover in the next lecture before we move on to bosons. But before I do that, let's see if there's any questions, and then I'll take the attendance, okay?
Sir, on the ultraviolet catastrophe part,
Yeah.
the quantum mechanical curve, the line, that also goes to infinity with the ultraviolet spectrum.
No. So this line is not this is just the line that is plotting the maxima of these. So these are the lines. I should have used a different color here.
Oh, okay, got it.
Okay, yeah. So let me use, let me use a different color for this thing. Can I do this? Let's see. Apparently not. I wanted to select just this guy. Apparently I can't. Yeah, so so this should have been, I should have used a different color. I should have used this color. The ultraviolet catastrophe would follow this curve, but then it would go up like this. Okay, that's the classical analysis.
So what happens in quantum mechanics that produces the dip?
Yeah, what happens is that so you see that, for low frequency, it's a good approximation, the classical thing, right? It's really the high frequency. In the high frequencies, you're getting more and more contributions from the classical, oscillators. But what happens in quantum mechanics is that because the oscillator energy expression is E is equal to NH bar omega, right? So for large omega, the differences in subsequent, subsequent energy level is quite large. So what happens is that it becomes harder and harder to excite this higher frequency modes. And that has the effect of naturally regulating the energy that is going to go into the higher frequency modes.
So in classical mechanics, it would be that they're all just as easy
Exactly.
to excite?
Exactly. And it has to do with classical equipartition of energy, and yeah, that's very. If you're interested, I can send you. I think I did a lecture on how the classical thing works out, and I can, for a previous course, I can send you that.
Oh, I would like that.
Okay. Okay. Any more questions?
Sir, the particle in a box, is the box physical, or that would be that can be imaginary as well?
Well, the box can be anything. The box is just one way of like making sure that the particle doesn't get out. It can be a potential. So, for example, you can have like a, I don't know, like a harmonic oscillator, which is a quadratic potential, right? And if you're looking at just the, at the energy states lower than a certain energy states, that you can say, okay, can I? Actually, the harmonic oscillator is very special. Yeah, it can be a physical box, but it can also be a box that is that you do an approximation by a box, and then you let the size of the box go to infinity. So,
Sir, doesn't the wave equation pass the box, pass the boundary of the box, so that the quantum can tunnel through the box? The
well,
quantum
yeah, there are
particles?
boxes of there. So this is like this is a box whose potential is infinitely deep. So in that case, this is the potential. So this goes all the way to infinity. So you can show that for such cases, the wave function cannot seep out. But if the box was of finite depth, if it was a finite potential well, then the wave function can go out. But here, mathematically, you can show that for the Schrodinger equation to be well defined, the wave function cannot go out. Otherwise, the Schrodinger equation is not well defined, because the Schrodinger equation has in it a term with d in it, and if that v goes to infinity, that Schrodinger equation, at that point, psi has to go to 0. Otherwise, the Schrodinger equation there doesn't make sense.
So the box is just a potential well.
Yeah, it's an infinitely deep potential well. Yeah.
Okay, got it.